Hey folks, I want to do this quick video on exponential function, complex numbers, Euler's formula. I'm going to do this in one take, so I apologize in advance when I don't word good. Okay, so let's get started. Hey, why do we care about complex numbers or so-called imaginary numbers? Well, I don't really like to use that word. We have real numbers and we have imaginary numbers, but I always put these things in quotes because they're not really more real or imaginary than the other. They're just data representing something hopefully useful in real life. And for complex numbers, a combination of a real part plus an imaginary part, uh, I view this as two-dimensional information. You have an x and a y coordinate. Okay, so you can think of it as x plus iy, or just the coordinate x comma y. And the reason that we like imaginary numbers, because this seems kind of redundant right here, why don't we just write it as an ordered pair? Well, you might remember polar coordinates, right? Which I always put a p before mine to emphasize that it's p for polar, but a lot of folks just know that if you have an r and a theta, we're assuming that we're talking about polar coordinates. And so that would represent this length is r, this angle is theta. And the great thing, the very cool thing and the very useful thing about complex numbers, why should we care about I, that square root of -1? It doesn't exist as a real number, but it is useful because turns out if you can compute the real number r, that radius length, times e to the I theta, that's exactly the same complex number as x plus iy. And so if for your application it's easier to describe a point in terms of how far away it is from the origin and the angle it is from the x-axis, well then you have a very nice slick way of crunching those numbers in terms of the exponential function e. And so let me convince you of this real quick, because it's not at all obvious at first sight why that has to be the case, but it's not hard if you know a little bit of calculus too. What you can do here is you can take the series expansion of e to the x, and so that r is just going to stay still for the entire proof. But e to the x, if you remember from calculus 2, you can write it like this: 1 plus x, so our x is I theta, plus x squared over 2 factorial plus x cubed over 3 factorial, and we'll just do this forever. And we can simplify this. This is why the square root of -1, this I thing, is actually really powerful and really useful, is because we can simplify this formula, and I'm just going to, well, that's just an I, so I'll just leave it like it is. But if I is supposed to be the square root of -1, then I squared, that should be a -1. So we're left with theta squared over 2 factorial. Here we have 3 i's. 2 of the i's make a negative. The extra I sticks around. Theta cubed over 3 factorial. And then you can do this a few more terms, however many you want, to kind of see what's going on there. But what I notice when I do this is I can rearrange this. The r just is going to stay there the whole time. Don't be surprised by that. But I could take all of the things that do not have an I. So like 1 minus theta squared over 2 factorial. If we kept doing it, we'd get theta to the 4th over 4, theta to the 6th over 6 factorial, and that would happen a long time. And then we also have the I stuff, which I'll just take down here. So the i's, I'll factor those out. We're left with a theta. Here we have theta negative theta cubed over 3 factorial. And then if we kept going, you would have a theta 5th over 5 factorial minus 7 factorial. All right. And so what's the point? Well, again, you have to know some calculus too. This is why we spend so much time going over sequences in the series. Turns out that they're useful. And the useful thing here is that this 1 minus theta squared over 2 factorial plus, if it's the even stuff and it's alternating positive, negative, this is just a big fancy way of just writing cosine of theta. Okay? That's all this stuff right here is. Likewise, if it's the odd powers, alternating positive, negative with these factorials on the bottom, that's just sine of theta. We have that plus I there, so let's write that down like so. And so what we've done is we've taken re to the I theta, and we've rewritten it like so. And then, but what does that have to do with x plus iy? Well, remember, how do we get from polar coordinates to xy's? We'll just factor out this r. Now we're actually going to use the r. We get r cosine of theta plus I times r sine of theta, because that r splits over to both. And then there's my x. R cosine is x. R sine is y. All right, so there is my, I've proven it for you. I've proven to you that you can describe any polar coordinate, sorry, not polar, complex number in terms of r e to the I theta. But this allows you to think of it in terms of polar coordinates. All right, but in practice, the real important part is this piece right here. If I'm going to actually crunch the numbers, this is what I use to compute things. In fact, it's so useful that I often use a shorthand. Instead of writing out cosine plus I sine, I'll just write CIS, cis theta, which is a short way of writing cosine plus I sine of theta. And let's put this to use, all right? I'm going to use this to calculate two things. Let's take e to the pi over 2I minus 3. And to do this, well, first thing we notice is that we don't have it in the right format. We don't have it as re to the I theta, but you can always get that because just split up the imaginary and the real parts. So e to the negative 3 would be the real part. E to the pi over 2I would be that imaginary part. And then what I can do is I can write this is just the real number 1 over e cubed. And then for e to the pi over 2I, or ei pi over 2, same thing. I'm going to use this piece here. I'm going to write that as, I'll write it as cis pi over 2. All right, which is really just a middleman. I can expand that, and in fact I'll need to expand that to simplify it further. That's cosine of pi over 2 plus 1 sine of pi over 2. And then now, since I know a little bit of trig, I happen to know that the cosine of pi over 2 is nothing. That goes away. Sine of pi over 2 is 1. So I just have, this is just an I right here. This is just going to be 1 over e cubed I. That's it. So it turns out this number is actually purely imaginary. It just goes up in the I direction on the xy plane. Okay, and then we can also get other nice properties. For example, what if I want to know what the hyperbolic cosine of 2ix, that's a function. Does it simplify to anything reasonable? First of all, we have to know what the formula for hyperbolic cosine is. It's just in terms of the exponential function. It's e to the whatever plus e to the negative whatever, in this case 2ix. Divide all that by 2. Okay, and then I can pull out that 1/2. This I could rewrite as cis 2x. This is plus cis negative 2x. But again, if I'm going to want to simplify, maybe I think I can simplify this. We're going to get cosine 2x plus I sine 2x. And then for here, for the negative 2x bit here, it's going to be the same thing, but I have to remember things like cosine of negative 2x. Well, cosine's an even function, so it swallows up that negative like an absolute value. And then for I sine of negative 2x, it's an odd function, so that negative comes to the outside. All right, and so what that tells us is that here we have I sine 2x canceling with the negative over here. I've got two of these cosines. Now they have the same thing. So 1/2 times 2 cosine 2x. Hey, it turns out hyperbolic cosine, you stick this I in there and it's basically just cancels the h. It doesn't really do it. You don't do that. That's dangerous. But it turns out in this situation that the I gets swallowed up by the hyperbolic part, turning it into regular cosine. These things actually have something to do with one another, which is, I think, something that's kind of crazy that doesn't get covered as well in calculus as perhaps it should be. This is why we call it hyperbolic cosine. So that's the really quick crash course and how you can use the Euler formula again. Here is what we'll use right here. a lot of the time if we have an exponential function with a complex or imaginary power right here. The other thing I'll toss up here really quick are just some other formulas I grabbed off of Wikipedia actually. Here they are in the middle of the screen, and these are all things that you could prove just like I just did. In fact, I just did prove this one right here. Oops. Right here. This is the same thing I did just with 2's here, here, and here. So you could prove all these, but they're very useful shortcuts. If you're doing a lot of work with these sorts of formulas, it might be worthwhile to keep this in mind. All right, so I hope that helps you out with using exponential function and complex numbers.